Welcome and thank you very much for joining the Liverpool Omdina chapter. This is our second project, and the very first project we did was basically a classification and sort of regression problem as well, included things like time series and whatnot. And this time we thought we'd go with a computer vision task, simply because computer vision is quite an interesting subject. There's a million different use cases for it, and it seems to be quite popular in the medical industry at the moment. So I thought, using a quite a relevant subject and trying to create something that will do, the world good. It'll give beginners and people on the project a lot of experience, and overall, it's like, because it's based around children as well, I think it's good to give back. It'll be really interesting, and hopefully we get a lot out of it as well. So the title: Detecting Pediatric Acute Lymphoblastic Leukemia Using Computer Vision. So today I'll talk about the team who are going to be basically managing the project. I'm one of them, of course. I'm the chapter lead. We've got the background to the problem itself, what we're trying to solve, the project goals in terms of what we need to do and what we're going to learn, a bit about the data that we have, the project plan in terms of the sort of timeline, the benefits of being on an Omdina project and generally being on this particular project. And then at the end, we've got time to discuss any questions anyone has as well. So let's get into it. So introducing me, and I hate talking about myself, but it has to be done. I've been working in the data field for around 10 years, and I started as a management information analyst and basically worked my way up, following different kinds of interests, eventually discovering machine learning and finding it very interesting. I wanted to know more and made the move into machine learning in around 2019. It was really the end of 2018, but I really started working hard at it in 2019. I've had, a number of different experiences with things like computer vision, NLP, and things like that. 90% of machine learning is regression and classification, but a lot of people specialize in one area, but I quite like the lot of it. So I've dabbled in numerous different sorts of domains and tried my hand at solving problems in work and outside work as well. I'm very much a believer that machine learning and artificial intelligence is obviously going to shape our world for the greater good, and I'm looking forward to that. And hopefully, one of the reasons why I like to host challenges on Omdina is to help people get into this fascinating and exciting industry as well. I think it's something that everyone should know about, and if possible, work in as well. It's very rewarding. You'll be, if you make the move into machine learning, data science and whatnot, you'll be a lifelong learner. You will learn every single day until you depart this mortal coil. It's fantastic. And it's going to be our future. So why not get involved? Okay. Salman, he isn't here at the moment, but he is the co-project lead and also the lead on learning and development. Now, a lot of you may have know Salman from LinkedIn. He's very active on there, posts a lot of various different bites of knowledge that people like to share. But Salman is been in the AI and machine learning industry for around 12 years. He's got 7 publications that have been published in peer-reviewed journals. He gives seminars. He's done some guest lectures around machine learning and artificial intelligence as well. He's a certified TensorFlow developer. So he has a lot of experience using the TensorFlow mainframe. Is that the right word, mainframe or framework? That's probably better. And he's a technical reviewer for the book TensorFlow Developer. He's got fantastic experience in computer vision as well. And of course, we run a YouTube channel where we discuss things and try to teach people about machine learning in a very light-hearted and fun way. Well, we certainly think that's the way it is. We don't like being very serious about it. Learning's meant to be fun, so we try and capture that within our sort of mantra. Okay, so the problem that we're going to solve, we need to take a look at that. So the background, acute lymphoblastic leukemia is basically an accumulation of immature lymphocyte precursor cells, typically known as blast cells. The buildup eventually disrupts normal blood cells, and it in the bone marrow, and it reduces the number of red blood cells being produced, as well as white cells and platelets too. So this particular type of leukemia, it's the only one that's more common in children than it is in adults, and it's the single most common form of pediatric cancer, and it accounts in the UK around a third of all cases in children. 400 children in the UK a year get diagnosed with it, which is obviously way too many. Most commonly between the ages of 2 and 4. So it's, you know, it's a common leukemia, and 400 children who are between the ages of 2 and 4, you know, they're the ones who are most likely to be diagnosed with it. So it's really not great, especially at such a young age too. Males are affected more often than females as well. Now, for this project, you don't need to be a cancer expert. You don't need to be an oncologist. We just need to know the basics about it, because, you know, them expertise can be left to the experts who will be examining our results and examining maybe the accuracy of our model, and giving us some hints and tips of how to improve that, and just generally, you know, assessing how good it is. Now, the problem that we have is that the task of identifying immature leukemic blast from normal cells under the microscope is challenging due to morphological similarity. So the diagnosis can be time-consuming and costly. Now, you know, just looking at these cells through a microscope isn't the only way this disease can be diagnosed, but it is a large part of it. In the medical industry, you know, what's it called? Electron microscopy. I can't talk. And you know, basically getting visual images and physical structures of the particular pathogen, or you know, in our case, blood cell that's been sort of infected, or it's grown into cancer or whatnot. That is part of the diagnosis process. And from my research, before putting together this particular project, it was the part of the process that took the most time, basically, because it is quite difficult. So I thought, let's see if there was data there that was available. Let's see if we can build something that could help in that process and make it a lot more smoother, a lot more quicker, and perhaps even more accurate. So that's the problem. We need to diagnose cancer and from blood images, and these are single cell images as well, which I will show you now. Okay, so the project goal. The goal of the project is to build a computer vision model which will make early identification of pediatric ALL not only accurate, but quick and cost effective, and it allow early treatment to be sought and potentially save the lives of those who are affected. So the key to surviving cancer is getting it early, and hopefully we can you know, reduce the time of diagnosis with our model. Okay, so the data. Now, the data are microscopic images of blood cells. They're representative of real blood cell images, because what we've been able to do is leave some of the staining, noise, and illumination errors in there. Some of them have been fixed. You know, they're not completely raw images. Some of them have been slightly processed just for the ease of our use, and it would save us a lot of time. We have 4 to 5 weeks I mean, that's not strict. It could go on if we choose to, but 4 to 5 weeks, we wouldn't have had time to clean up 15,000 images. So it's already been done to a certain extent for us. Okay, so there's 15,000 images from 118 patients, and they come in 2 classes, a normal cell and a leukemic blast. So one with cancer, one without cancer. Now, the training, it consists of 3 folds, each with around 2,500 positive samples and 1,000 negative samples. So we do have a slight class imbalance, so that's something to think about. The validation contains 1,800 images with a ground truth CSV file as well, and all of those have been confirmed by a childhood oncology expert. So we do have the reference to which images are the ground truth basically of every one of our images. So it'll be great for a validation data set. The testing, now, because these come from a sort of medical facility, the testing images don't actually have any labels whatsoever. So we won't necessarily have to use them to, we can obviously split our validation into smaller chunks to use for our model. That's not a problem. But the real test of how good the model does is on completely unlabeled data. We can run a selection of these images through, and we can basically see if our predictions are correct by contacting the oncology expert and see if he has, can verify our model is correct. So it would be a true test of how our model is performing outside the validation. So that is one to think about as well. When we're building the model, developing, the various different parts of the model, we can ignore the testing for now because that's our true test. We will get to that when we're done, and we can possibly deploy the model too. So that's what the data is composed of. Now, this is what the images look like. So this one has this one is cancerous. This one is normal, and as you can see, there's non-diseased, diseased, non-diseased, diseased, diseased. So, other than a couple of sort of physical attributes between the there isn't really, just looking at them and being not an expert in this kind of thing, it's quite difficult to determine the difference between the two of them. And this is where the computer vision model can help us with that. Now, that is just, I just wanted to demonstrate what the data looks like. And there's 15,000 of these images. So when you see these pictures, you might have a couple of thoughts running through your head. How can we improve these images, maybe cut out the black space and things like that, just to get most out the model? These are the kind of things that we need to discuss as a team later on in the project. The first week, we will generally, I'll give you a couple of days to look at the data, look at the images, take some samples, research augmentation techniques, research how to improve the fidelity of the images that will sort of, that will benefit the model. All them kind of things over the next week. These, is what we need to think about. So this brings us to the project timeline. As I've just said, week 1, data explanation, analysis and discussion. Go away, look at the data. Let's see what we can find in there. Is there anything interesting that you've noticed? Take a look at, research computer vision models, specifically in the medical industry. What kind of models are they using? What's the architecture like? What kind of pre-processing do they do on their images that get input to the model? Is there anything we can apply to our images? Has anyone done anything similar before with blood samples? Can we learn anything from that? And then bring all them ideas and let's discuss it as a team, and then we can work out a way forward. Now, that doesn't mean to say there's only one way forward. I know of around 3 or 4 image augmentation packages that operate outside of TensorFlow and PyTorch. It could be that we have a team, a team of 3 teams, and we try different augmentation tactics in each one of them teams and see how it, and how how the results of the model differ between these two teams and the different sort of techniques we've applied. There's a number of different ways we can tackle this project, and I want to leave that open to discussion. We do have quite a number of participants, and it doesn't make sense if we all work on the same methodology. You know, I think we will get a lot of benefit out of splitting splitting into groups of 10 maybe, and all trying something different, and then we can, that will be an ultimate learning experience on that. So, these are the kind of things I want you to think about in the next week, and gather some ideas. Let's gather some interesting techniques in the medical field. Let's gather information about data augmentation as well to see what we can do. Now, week 2, that's when we properly begin. That's where we pre-process the data. We apply any augmentations we've discussed, and what we call a feature engineering as well. That's what that part is in terms of our images. That's what we do. That we'll try a number of different techniques, and we can compare them across our teams if that's the way we want to do it. Week 3 is the model development and testing. So that's where we begin to start to build our architecture. Now, this one, there's a number of different ways we can do this. We can create completely custom models, not a problem. But there's also techniques like transfer learning. We could use a ResNet 50 to do a feature analysis on the images and pull feature information out of that, and then treat it as a classification problem by using a gradient boosted tree. So, there's just a million ways we can do these kind of things, but that's what we need to decide. How are we going to attack this? What team will cover what? And then we can compare all the results at the end. And I wouldn't say it was a competition, but the best model wins kind of thing. But it's an interesting learning experience for all of us if we try different techniques. We've had great success in previous tasks by doing that. The best way to learn is to just throw everything at it. Let's try a number of different models. Let's try a number of different techniques, and that will benefit us all. We'll get a much more broader idea of what goes on in the real world with computer vision, especially around the medical industry. Then week 4, deployment development. Now, the problem we're trying to solve is to benefit people who have to diagnose children with these cancers. We want to take as much hard work away from them as needed. The job's hard enough. Now, the model deployments, there's a number of ways. Do we really need to deploy it? No, because we're in a beginner's project. This is about learning. However, part of the process, if you were to work in real life, is businesses want their model deployed in some form. Do we create an app for a phone? Do we create a web app, host it on Flask? Do we host it on Streamlit, where we can drag and drop images in and it'll give a prediction? These are the kind of things we need to ask ourselves. There's no right or wrong answer here, but we just have to be we need to watch our sort of audience. We want to do this, maybe a Streamlit app is more than enough just to demonstrate our work. The second part to it as well, this project is for your portfolio. So this work and all that it entails will be a good project to include, and that will be, you can write about it, of course, but it's nice to have something that you can show someone as well. So deploying it to a Flask app, deploying it to a Streamlit app, it's a good idea. The last project we did, we deployed a Streamlit app which basically documented every stage of our project. It talked about what kind of things we did, what the results were, and had like a sort of interactive map that people could take a look at and see what our findings were, and really analyze the output as well. It's a good idea to have, and if you just write in your resume, I'd done this project and it was computer vision. We diagnosed cancer in children. Fair enough. Yeah, that's great. But if you've got an app that's being deployed to Streamlit, you can say, go and take a look at it. It's impressive and it helps a lot in my experience. And then week 5, after the development is being done and finalized, we can launch the app. Let's see if it works. Let's get it on LinkedIn, pass it around, let people use it, let people test it, and see what they think, and see what, and give the feedback and make any amendments that may come in. But again, because this is designed for you to have in your portfolio, when week 5 comes and the app is launched, that doesn't mean you need to stop working on it. You guys can develop that and take that further if you choose to. At the end of the day, it's up to you. It's your portfolio. It's your project as well. So it's completely up to you. And in week 5 as well, we do the final presentation. Now, I mentioned earlier that we usually meet twice a week, once at the weekend and once through the week. The weekend is usually to sort of reflect on the previous week. The midweek one is just a check-in. Is anyone having any difficulties? Is any, what have people learned? Has anyone got any ideas to put forward to the team? And it just, gets us talking, kind of thing. Of course, we've got Slack. Keep Slack active. Post as much information in there as possible to the benefit of you and your teammates. But I think having a face-to-face call is beneficial as well, where we can speak about it live. The people we have on this project, the experience levels varies. We have some complete beginners, but we have people who are already working in the computer vision space as well. So it is a great opportunity to learn from each other. And, there's some questions that, I might not be able to answer, but someone who works in, the computer vision in the medical field, who is on our project, will be able to answer that question. It's a fantastic opportunity, especially with the level of talent we have on this particular project. Okay, so the next part is the task leads and co-leads. Now, each task, apart from week 1, requires a voluntary lead. And what they're responsible for is collecting ideas from the team, producing the code, refactoring other people's code that has come in as a suggestion, publishing the notebooks to the GitHub, and presenting the findings at the weekend as well. So the weekend calls, say if we're in week 2, it's data augmentation, feature engineering, or whatever you want to call it. Say if we split into 3 teams and we all take a different approach. Someone uses horizontal flips and vertical flips and whatnot. Another team uses the hue and saturation, changing the colors of the images to see how that affects. And the 3rd team uses cropping, resizing, and whatnot. Now, each of them tasks will have a team lead who's responsible for implementing them. Of course, they're not completely unsupported. The team will support them in producing these outputs. And then on the Saturday, each 3 of them teams, will present what they've done and how they've done it to the other team. So they pass their knowledge on, and let's learn, from each other as well. So that's what the task leads generally do. It's better for a task lead to have more experience because they are fundamentally responsible for their particular week of action. And the co-lead is better suited for someone with a lesser experience, simply because they will be supporting the task lead, collate the ideas from the team, doing the coding and understanding exactly what's going on. So you're sort of like a sidekick. It benefits you, but it helps you sort of project manage as well. Talk to your team, listen to the suggestions, and put them to the task lead, who can make that a reality as well. So what I'll do after this call, I will basically put a form out with each of the weeks. And if you want to volunteer to be a task lead, write your name down. If you want to volunteer for a co-lead, write your name down, and I will select them completely at random, just to make it fair. However, that doesn't mean, and if we split it, we can discuss this more in the Slack channel or at the end or whatever we want to do. If we want to split into a group of 4 teams, if you are a task lead of them particular teams, That's great. You've got responsibility of a team, you're project managing that particular team and that subset of tasks. If you're not a project manager or a co-lead, that doesn't mean you can't help other teams work on their particular strategy as well. So if you're on a team who's going to use transfer learning and use a ResNet 50 to extract features from the images and treat it as a classification task, that doesn't mean you can't go and jump in and help another team who are building their own custom convolutional neural network. It's all about learning. If something that you see interests you that another team's doing, join them. Join their side calls. Speak to the people on the team, ask questions. That's what it's all about. It's collaboration from everyone. There's no competition at all. There's nothing like that. The more you get involved, the more you speak to people, the more you're going to learn at the end of the day. And this is the perfect platform to do that, and it's the perfect opportunity as well, especially if you're interested in computer vision. Okay, so the benefits of becoming a collaborator: it's a safe space. This is an opportunity to work on a real life project where it doesn't matter if you make mistakes. It doesn't matter if you think you've got a stupid question. There's no stupid questions. We're in a place where everyone's on the same page. Everyone's here to support one another. If you make a mistake, so what? That's how you learn. You don't learn anything by getting everything right. I'm terrible. If I try 10 things, only one works. So that's just the way you have to learn, and this is the perfect opportunity to do that. I want you to make mistakes. I want you to make mistakes more than you do actually any good work, because that's just part of the process. Machine learning, data science, it's completely iterative. It's always going back to square one all the time. When you find out new information, you get more data, or you mess it up completely. That's part of it, and there's nothing wrong with that. But it can be, especially in the medical industry, if you create a model that's no good and someone gets, diagnosed with cancer, but they haven't really got it, that's when you start losing your job. Fortunately, this won't happen in this particular space. It's fine. We can make them kind of mistakes because we learn from it. As well, employment. You will, by the time you come to the end of this project, you will increase your data science and machine learning skills. You become more employable. You get a project that is perfect for your portfolio at the end of it. And of course, you get the sort of skills of leading a team, project managing, presenting your ideas to a wider group of people from all different backgrounds, all different domains of expertise, and of course different time zones as well. So you get that experience, and that will benefit you a lot. Being a data scientist and machine learning, it is a technical. They are technical roles. Technical skills go a long way, but if you can't explain or convince people of the work you've done or your technical prowess, there's no point. You need to be as good socially as you are in technical to explain to a layman the problem that you've solved. 99% of the time, your stakeholders are laymen. They just want to see results. They want to see profits increase. They want to see. They want to know how you've solved the problem. Are they going to want to know the inside out of a convolutional neural network? Absolutely not. But they want to know how it works in a nutshell. If you can't explain that to them, there's no point. So this is also an opportunity to improve on them skills as well. Presenting skills are very important. It's funny I say that because obviously I can't talk and I keep stuttering and mispronouncing all my words. I don't know what I'm talking about, but it's just one of them things. And of course, your verified certification as well. You get that out of it, and a year-long subscription to DataQuest. DataQuest is a fantastic platform where you can learn various different skills, data engineering, data science, and machine learning, I think, and Python programming. It's really good. I had a year-long subscription to it as well, and it was, I thought very, very useful. But unfortunately for me, I learned the hard way. There was no sort of platforms like that when I started my career, so I just had to break everything to learn, and nearly get sacked a few times. But here we are. Here we are. Okay, and that brings us to the end of the presentation. Now, before we get into any sort of questions, what I'll do in regards to the meeting times, I will put out a small survey where you guys can pick whatever times you are more comfortable with meeting through the week and at the weekends as well. And with that, I'll just have to go with the answers which have the most votes, basically. But of course, again, don't worry about it. If there's ones that you cannot make, I'd suggest make the meeting, prioritize the weekend meetings over the midweek ones, because as I say, the midweek ones are only like a sort of check-in. The weekend ones are where we reflect on the weekend. There'll be a lot more content heavy. But again, you know, life gets in the way. I know we've got kids, we've got jobs, stuff goes on. If you can't make it, I make sure I get the videos on YouTube within 24, 48 hours. I always drop in and say, this meeting's being recorded, it's on the YouTube there. So if you can't catch up, if you can't attend on the day, catch up, don't worry about it. So is there any, let me just see, you know, I've seen that there's been quite a number of chats going on. Let's take a look. I'll tell you what, we've got 3 minutes left in this call. Let me just see what we're doing here. Dr. Shai, I hope that's the way you pronounce your name. Hi, we just completed the Jordan Acute Lymphoblastic Leukemia detection using deep learning models. Recommend YOLO and large high-res data sets, accuracy, efficiency. Yeah, nice. Yeah, I've seen that one. They used full blood, what are they called? I can't remember what they're called now, but we're using single cells. So it's slightly different, but yeah, feel free to, like, we can try these techniques. You know, it's great. It's great that you've done something before. So let's write all that down and we can take a look at that. It's perfect. Image pre-processing, adjust image color. Yeah, spot on. Watershed to dilute image. Yeah, cool. So this is all the kind of things we need to think about in our first week. Okay, let's take a look. Data set, yep, 15,000 images. It's already labeled. The training data and the validation data is, but the test data isn't. Okay. Yes, the data set is linked in the problem statement channel. It's on my Google Drive. Everyone should have access to that. It's in a zip file. It's in the training data is in 3 folds. So if you haven't got the greatest, most powerful laptop in the world, by all means, just look at one of the 3 folds. I think the 3 folds have the same amount of images in them, 2,500, I believe. So there's enough there to do some experimentation and augmentation on them. So yeah, take a look at that.
Hi, Rich. I just missed one part. Like data set is available in problem statement.
Yeah. So if you go to the Slack channel, the problem statement channel, there should be bookmarks at the top, and it says, sorry, my laptop's going a bit slow here. It says image data. If you click on that, it'll take you to the zip file in the Google Drive. You can just download that and take a look. Yeah, so it's all there.
Thank you.
In terms of the GitHub, I need to invite, for some reason, GitHub doesn't let you do a blanket, an umbrella sort of invitation. I have to invite people individually. So I'm getting my way through that. I've invited about half of everyone on the project. I eventually will. I'll do it over the next couple of days. So don't worry about that for now, because we don't have to use the GitHub for now. So yeah. So give me. I'll tell you what. Let's restart this call. We've got about 30 seconds left. So if you leave the call and refresh, I'll restart it, and we've got another 45 minutes then. Okay. So I'll see you in 2 minutes. Okay. I'll just give it a minute so everyone can come back in. Now, has anyone got any initial questions at all at the moment? Yeah, okay. I've got a question. Where can we be looking if we are CV beginners? Now, that's a good question. So in our Slack channel, I've created a channel called Knowledge Sharing. If you could go into that channel, what I recommend everyone does, and I will do it too, is share various different articles about computer vision. I will share useful GitHub repositories, and also alongside, obviously, us collectively sharing knowledge between ourselves. Salman will be hosting calls as well to basically demonstrate how to augment data, image data, and how to employ various different techniques, how to build a custom model, how to use transfer learning. All these calls will be booked in with Salman directly over the next few weeks. They will be specifically designed for someone who has no idea about computer vision. So if you are a beginner, I would recommend joining the calls that Salman will be hosting. You'll receive more information over the next week about the first call, because it is really good as well if you are on a team and you don't really understand something, and what Salman can do is show you how to do that step by step and guide you through that, so you have a better understanding of what went on in the previous week. We've done it for our last project, and it was really useful. Unfortunately, Salman got COVID, and we had to cut those sort of sessions short. But hopefully this time, there won't be any issues at all, and we'll be able to do a good few of them. Yeah, they are really useful, but Salman's really, he uses, he has a lot of experience with GANs as well. So, it'll be a mixed bag of different experiences for you, and it'll hopefully benefit you and put everything about the project into context. It'll be fantastic. And by all means, a lot of the people who are on this project who have a lot of experience, if you take a look at the Introduce Yourself channel, there's some really experienced people in computer vision. And I'm sure we're all working for the same goal. We're all trying to do the same thing. Feel free to reach out to these people. Feel free to reach out to me or Salman. I work full time as a data scientist and machine learning engineer, but I'll always make time for people who have questions. I might not answer instantly, but you won't be waiting more than a day for a full response from me. So feel free to reach out if there's anything whatsoever that you are confused about. We're all here to learn. We're all here to work together. The knowledge sharing channel has been a great success in the past. If everyone shares interesting research they found, interesting techniques they found, or there's a million different ways of doing something, and the medical industry has a lot of research into computer vision for diagnosing various different ailments and disease, in the lungs, in the brain, in the heart, or whatever it may be. Share those research papers, share the code, share the data sets. We can come together and build a good head of knowledge and put that into practice by doing it and producing our own model, producing an app that can detect childhood cancer from blood samples. It's the best way of learning. Okay, the knowledge channel is in there. What I'll do right now in the meetings channel, I will tag it. Knowledge. It's a hashtag, isn't it? Not an @ sign. There we go. So I've just shared it into the meeting where everyone's in, the meetings channel. You just click on that, you can join it. It's not a problem. Okay. Any other questions at all? Oh yeah, Gary. Okay. So now let me just go back to my presentation. The data set, it's of single images of blood cells. Let me just get my presentation back up and I'll share my screen again. And I'll just show you what the data looks like. Right, here we go. Where's my share screen button? There it is. Window, project, boom. There we go. Okay, so you should be able to see my screen now. So the training data consists of 3 folds, each with 2,500 images in there. Sorry, positive samples and 1,000 negative samples as well, which are marked all or hem respectively. Validation, it contains 1,800 images with a ground truth CSV file, which have been confirmed by a childhood oncology expert. Now that CSV file contains information like patient's ID and whatnot. It gives you a list of all the image names and what the diagnosis is. The training data, it's literally 3 folders with the images separated into 2 subfolders, ALL or hem. ALL is negative, hem is sorry, ALL is positive, is positive, and hem is negative. Hem is normal blood. So yeah, that's how the data is laid out and what it looks like. Let me just talk about the testing. The testing has 2,800 images. They're all unlabeled because this come from a medical institution originally. And of course, these images were supposed to be tested on. A prediction would be made, and then predictions will go to an expert in that field who will say, yeah, that's a correct prediction, or no, that isn't a correct prediction. But you know, there's interesting ways we could use that testing data. Now we could use a model that, you know, gives, you know, say if we use the testing data and we run the 2,800 images through our model, and we get, say, 800 images above a 80% confidence that they are positive, we can take those 600 images and we can provide them to an expert and say, would you agree with these? Yeah, where the data source comes from. I mean, would you agree with this diagnosis? I mean, that assuming he has time, but that will be interesting as well. We could try and, you know, based on our validation data, you know, if we get a model that's very high accuracy, we could test it on that and see if we could get 100 samples that have a confidence level of over 90% and see if we can put that to an expert. That is what they would have used the data for originally. But as we have all the data, that's why that's there. In terms of validating our model, it's going to be pretty much useless. But we can, you know, we can try some experiments with it and see what we think and see if we can get a second opinion. That is an option. But that's why I've included it. I did think about deleting it because, you know, but I thought, well, why not? Let's have some fun with it. Let's have some fun. That's what it's all about. So the images, this is what they look like generally. So this one particularly is a positive sample for leukemia, and this one is a normal cell. And as you can see, that there's a couple down here: non-diseased, diseased, non-diseased, diseased, diseased. So just visually looking at them, there isn't much difference. Some of them, like you know, I'm not an expert in cancer, but if I've seen that blood cell, I'd say there's definitely something wrong with that one. But is that a rule that we can stick to? Probably not. And that's why it is quite interesting, because, you know, we can figure this out. What makes, you know, what makes a cell visually cancerous? You know what I mean? It's like, we can analyze that sort of information. So we do have a good opportunity here. And we've got, as I said, we've had someone work on a similar project using a different kind of images, and they've already got some models that work well for them. Let's try them. Let's try them on our project. Will be interesting to see if them sort of performances can be transferred over. Let's try it. That's what it's about, experimentation. So yeah, that's what the data looks like. I hope. The CSV file, Gary, give me 1 second. If you're in the Slack channel, if you go to the problem statement channel, in the top bar in the bookmarks, there is a link to a Google Drive called image data. the CSV file is in the zip. If you download that, unzip it, it'll be in the validation folder, and it'll have the corresponding images in the validation set as well. That's where the CSV is located. What else do I need to say? I think that's pretty much it. What I want to reiterate is that this first week, what I want you to do is go away and download the data, look at the images, do some exploration of these images in a Jupyter notebook or whatnot. Research models used in medical imaging in a similar sort of way. There's a number of different papers on COVID-19 classification on lung samples. What kind of models did they use? Did they use TensorFlow architecture? Did they use PyTorch architecture? Did they use AutoML? Is there any that kind of thing? Take a look at what people are using to do similar kind of things. Take a look at blogs like Medium towards data science. See if anyone's done anything similar. Take a look at PubMed. Take a look at published work. See if anyone's using computer vision to diagnose blood diseases. Doesn't have to be cancer. It can be any type of disease. Is there anything that they do, or is there a particular model, or you know, do a good website is Papers with Code. Take a look at that, because it gives you what the research paper is, but it also gives you the implementation and code. Is there anything there we can use? Let's do our research. Pop what you find in our knowledge sharing channel. Share it with the group. Give the beginners, you know, if you're a beginner, take a look at that channel. Use the resources people have posted in there. I will be doing it as well. I've got a couple in mind about data augmentation and image augmentation. There's a couple of Python packages that, you know, I mean, you can do image augmentation within TensorFlow. You can do it within PyTorch, but there's also packages that allow you to do it before your model even sees that data. So, you know, that might be worth doing. And I believe they're a lot more powerful than the ones that are just available as like the image data generator in TensorFlow. There's things that these packages can do that TensorFlow or PyTorch can't. So, you know, they are definitely worth exploring in our project, and I'll post the links to them. But yeah, that's generally what we need to do in this first week. I will also as well post out a poll, as I mentioned earlier, for the best, so people can vote for the best dates and times for the midweek meetings and the weekend meetings as well. And we'll just have to go with which ones are the most popular. We're across a number of different time zones, and that's just the way it is. We have to try our best to all meet regularly. Subscribe to the YouTube channel, so if you can't make the meetings, let's catch up on that. Let's catch up on that. It's a good place to take a look at the you know, if you've forgotten something out of an earlier meeting or whatever, you can quickly scroll through it very easily. There's a question there. Hey Rich, just to confirm, ALL folder contains means cancer positive cell, and that's correct. Yeah. I believe in the CSV file there should be an explanation of what HEM means and what ALL. ALL just means acute lymphoblastic leukemia. HEM means something else, and for the life of me, I can't remember off the top of my head. I haven't looked at the folder for a while, but I'll post that in the Slack channel. But it basically means negative. It's a normal blood cell. It's perfectly fine. So yeah, ALL are the cancerous ones. HEM are the normal cells. So as well, as I mentioned earlier, the classes are imbalanced. Do we need to do anything about that? Is there any models that will help us overcome that class imbalance? Do we need to, you know, create images to balance things out? Is that what the augmentation is going to do? It's them kind of things I want you to think about over the next week, and you know, jot down some ideas, and we can share them with the group, and we can discuss a way forward. I think the best way is to probably split into teams. Depending on how many people we have who want to actively participate, we can maybe have 4 teams who will each try a different pipeline of techniques. And then when we come to the end of the project, we can compare all them techniques, what worked, what didn't work, what was useful, what wasn't useful, and then we can decide which model we want to deploy based on what we've learned. That's the best way we're going to learn, I think, and we'll probably do that. So I will put something together like a Google sheet where we can nominate our teams and decide what routes we want to go down. I think it'll be a great opportunity if we do something like that. But yeah, so that's what that's what this week is: a week of reflection, a week of research. How are we going to tackle this problem? How are we going to solve it? You know, a lot of the time, these sorts of problems, you know, we can create custom models, but nothing, you know, scientific work and medical science is built on other people's discoveries, and it's just a chain of a snowball effect kind of thing. And that's what we need to do now. Who's done it before? How did they do it? What can we change to make it better? Got a hand raised. Basanth, is that how you pronounce it? I hope. Feel free to ask a question.
Yes, I had a look into the training data, means the folder. It has subdivided into fold 0, fold 1, and fold 2.
Yes.
What does that mean? Is the all data is one?
Yeah, I mean, that is just to make the data more manageable. Each folder has, you know, like 3,500 images altogether. We can use them to quickly run experiments. Instead of putting everything through the model and waiting on training, we can split it down into smaller pieces, just so we've got enough time to, you know, if people are using Google Colab, we can make that work. You know, using 3,500 images is a lot better than using 15,000. So it's that kind of, it's just for ease of use. You can run quick experimentations. Feel free to divide that to even smaller chunks. It's not a problem. It's just whatever. I just thought I'd make it a little bit easier for you to you know, run experiments and see what you can come up with, rather than running the data through every time. I mean, there's ways around that. You can create chunk sizes in Python and run it through the model in batches and whatnot. But just for ease of use, you can just focus on one fold for the time being. Run some experiments on that, and once you're happy with it, you can apply to the rest. That was the idea of that. There's no other sort of inherent meaning to it at all. If that's if you understand that, and that answers your question.
Yeah, I got it. Yeah, I got
Cool.
it. And I have one more question. Like here, we are going to only classify whether the image is a hem or is it all.
Yeah,
right?
Yeah,
it's like a binary classification, right?
Yeah, it's a binary classification. Yeah.
Yeah.
However, that is, you know, we need a binary classification. Of course, we need a yes or a no. Does this person have cancer or don't they? However, we need to include some sort of confidence level as well in them predictions. So, you know, we need to, having a model that isn't as confident in predictions, because these are life-changing decisions at the end of the day. And of course, cancer diagnosis is not just based on one image alone, but we need to get the model as accurate, and we need to be as confident as possible in that accuracy. So, you know, it is a binary classification problem, but we need to figure out how we are going to get confidence in them images. How are we going to grade them? Are we 100% confident in that being cancer? Yes or no? That we need to have that inherently within the model. As I say, it's people's lives at stake, basically. So if you think about it like that, you know, it might give you a little clue of how we're going to tackle that, how we're going to incorporate these confidence levels within our predictions. There's a number of different ways we can do it, but it is an important part of it. We need to be sure of what we're classing is accurate. Any more questions at all?
Nothing from my side. Thank you. Yeah.
Cool. There's one in. Okay. Anka, is that how you pronounce your name? I think it is, isn't it?
Yeah, it's right. Hi, nice to meet you.
Hello,
and,
nice to meet you.
Thank you for the presentation. It was very insightful. I just wanted to ask, as I'm very beginner in this domain, and understanding that this week is a week of understanding and exploring, But what are we expecting after this week? So how are we going to split? And if you can give a more exact or more granularity into the next steps afterwards, because I'm more interested into directly executing the steps than exploring. If you
That's cool. Okay, so the first week, it's just a knowledge gathering week. It's to digest the data, look at the pictures, see what we can find. Has anyone done anything else? Now, week 2 is where we use that research that we found and we try and incorporate it into what we're going to do. So the first week is data augmentation. So, sorry, the second week, after the first week, is data augmentation. So this is where we examine our images. We apply various different sort of augmentations to the data, so we can flip it upside down, we can color them, we can crop them, we can zoom into them and things like that, because all this does is make more data for our models. It makes our model look at the image in different ways, shall we say, and learn about the images a lot more efficiently. We can resolve the class balance in that way. If we've got a class, say if we've got 1,000 positive images and 500 negative images, we can create another 500 negative images by using augmentations and seeing how that works out. So that's what the first week is. It's augmenting the data. Salman Khalik will be hosting a call on that as well, to how to do it, how to code it up using various different libraries, using TensorFlow, using PyTorch as well. But that is the first week. That's how we're going to put that into action. All the research we do in week 1, we will discuss as a group and say, that sounds interesting. Option B sounds interesting. Week 2, let's put them into practice. Let's put them together and let's discuss how we do it. So that's how we're going to use all that knowledge from week 1 in week 2 and actually build something with it. But the week 1 is knowledge gathering only because it's beginning. I don't want to jump in straight away blind, if you know what I mean. I want to have the group discuss various techniques first. I can provide a couple of papers on data augmentation, and then someone who is a beginner can look at it and say, I see what that means now. And then in week 2, when someone is actually coding it and making them change it to them images, that's when it'll all come together, kind of thing. And that you've read the theory, now let's put it into practice. And that's how it's going to run throughout this now. Hopefully that makes sense. And it'll be a lot more understandable when we're actually doing something. I'm very hands-on. I don't learn by reading stuff. I have to do it. And that was my idea about that sort of setup is, let's read about it first. Let's get an idea of what we're doing, and let's see how it works in real life. And that's how we'll learn. But if you're a brand new beginner, don't worry about it. There's plenty of support here. Reach out to me anytime. Reach out to other people on the team. Take a look at the Introduce Yourself channel. There's a lot of people with some good experience in computer vision. Some people have done projects that are very similar to this one. There's plenty of support there. So don't feel shy of reaching out or anything like that. We're here to support you, and hopefully you get the most out of this project by the end.
Thank you very much. That's very encouraging.
Thank you very much. Thank you for being here as well. Is there anything else? Any other questions anyone has at all?
Yeah, actually, I have
Eva?
a question. Yes. So is it beneficial actually to learn more about the disease itself and, something more, the background, how they determine certain things in that disease? And
it would, yeah. It wouldn't hurt. Absolutely. We don't necessarily need an in-depth knowledge about the particular disease. However, researching the disease is a good idea because someone may have done something similar in the past to us. If you research the disease in the context of computer vision, you'll probably uncover a lot of research papers that people have done before. I know cancer diagnosis is big in computer vision. It doesn't necessarily have to be the same type of cancer. Computer vision models, they're all trying to work to the same thing. Let's diagnose cancer from various different body parts. But yeah, feel free to research the disease, but I wouldn't get too bogged down on it. I wouldn't, you know, try and become an expert in this particular type. That's not what we're here for. Understanding the disease is one thing, but, you know, learning how to diagnose it from the images is another. It would be beneficial if you do find computer vision related information about the disease, though. Definitely, that would be a big help. And if you find anything, share it with us. I'm not by any means an expert in the disease, so I'll be reading them and learning just as much as you. So yeah, please feel free to find some things like that and share it to the group. I don't like to pretend I'm the expert. I'm not a cancer expert. I'm not even a computer vision expert. I've used computer vision in my personal and working life, but would I say it's my area of expertise? Absolutely not. There's a lot I can learn as well, and that's why I was excited to see people who were eager to learn and see people who had more experience specifically with computer vision than me. I'm a jack of all trades, master of nothing, unfortunately, as the saying goes. So yeah, but yeah, feel free to do that, but try not to fall down the rabbit hole and learn everything about the disease. Try and keep it into the context of what our project needs to resolve, basically. But yeah, good question.
Thank you.
Cool. Anyone else got any other questions at all?
I have another one. Sorry.
Yeah, go on, please.
I was just curious, is there any plan to integrate this work afterwards in a, I don't know, in a clinic or in a lab to take it forward, basically?
Well, me and Salman have discussed what we're going to do with this because it is quite a state-of-the-art project. Me and Salman this project, we're going to throw everything we have at the we're going to take all the good, transfer learning models. We're going to take some custom models, and we're going to throw everything at the problem. Hopefully, we can try as many models as time allows, and we'll get a really good understanding from that. And what me and Salman are thinking of doing is writing a paper about it and say, this data set of single blood cells, we were able to throw these 5 models at it, and we got this the results. These are the results from it, where we could improve it, and we'll write a proper scientific paper about it. We'll go into the different types of loss functions that we can use, which ones worked, which ones didn't, and we can compare them, and hopefully we can get something at least ready for publication from that. Yeah, sound like a paper on model comparison. That's pretty much what it's going to be in context. Now, to be honest, it was an idea, and I think we've discussed. Me and Salman have discussed that before. Salman has written 7 scientific publications before, so we will be taking the lead on that. And of course, everyone in the project who makes a contribution will be a part of that process as well. And we hope hopefully it'll be a great paper, but Salman's the expert on writing them papers. He's an academic. I fell into data and worked my way up, so I didn't go through academia. I learned on the job. So he is the best person to ask about that. But that's what the plan is, to get a scientific publication if we can, and include everyone on there, because it'll be nice for your portfolio. It'll be nice for the research as well, and try and contribute something positive to diagnosing cancer in children at the end of the day. That is what the ultimate goal is. I've got an 18-month-old son, and I couldn't even imagine what I'd go through if that happened. And I want to make that, as less often as I possibly can. And that's why I think publishing a paper with that as well would be a great step forward. And hopefully someone recognizes that effort, and, it benefits you guys as well. So yeah, that's the idea. There's not going to be, maybe not for use in clinical circumstances. We're not going to sell this app to a clinic, but we want to post some research on it. And even if one person looks at it and think that's a good idea, you never know. Someone might see that paper and think, let's develop this further and do something about it. You never know, but that's the part. That's part of the fun. We'll make a positive contribution to society. At least on our deathbeds, we can say, I done something towards that, and that's what the goal is. So that's what we want to get out of it. In answer to your question, a scientifically published paper. But yeah, I hope that answers the question. Cool.
Yeah.
Anything else, anyone? We've got 10 minutes left on this call. If no one's got any questions right now, don't worry about it.
Hi, Rich. One question from my side.
Oh, hello.
Yeah, so I'm just curious to know how this data was collected. Like, it seems like
the data,
we already have quite...
it's actually a publicly available data set, but it is a very sort of niche data set. Let me just find, I can't remember if it's on the top of my head what the establishment was. Give me 1 second. Should have had all these links ready, really. I should have preempted these questions, but there we go. Give me 1 second. Where is it? Because I haven't got the data set on this particular laptop. You see, it's on my personal computer, so I haven't got all the references there. But it was collected. It was collected from a university. Where are we? So the paper. Give me 1 second. Right. I'm going to post it into the chat. Here we go. So that was where the data come from, the Cancer Imaging Archive. And there's publications that use the data set who've done not exactly the same as what we've planned to do, but they've done things similar. They've used convolutional neural networks. They've used sort of, what's this one? Geometry-inspired chemical and tissue invariant stain normalization. So they've done, things with machine learning. They've done things with AI, but no one's actually really done what we plan to do. Image segmentation has happened on these data sets, and that's why I thought that might be an idea to tackle. So yeah, that's where the data comes from. It's publicly available, but I haven't seen anyone do much with it. So that's why it's nice to try and do something with a clean slate. I mean, you can go on Kaggle and find loads of different cancer images on Kaggle, but there's a million different notebooks all trying to do a similar thing. If this exists on Kaggle, I don't know. I haven't checked. I downloaded it directly from here, but I don't want to check because I don't want to be influenced by other people's work, if you know what I mean. I want us to try something completely from scratch. There's absolutely, if you want to look at Kaggle and see if it's there and look at the notebooks, do it, learn something. But, I think us bringing our own expertise and trying to solve it ourselves is very helpful, using other sources. I don't want to get stuck in the Kaggle sort of rabbit hole where we only use things from Kaggle and things like that. It's much better to explore it ourselves and make mistakes. That's part of the learning process. So yeah. Sorry, Gary, the image segmentation, that was basically a published paper using this data set. That's not something we're going to do. On the link, I think it's Rahul Duggal and a few other, they've done overlapping cell nuclei segmentation in the microscopic images using deep belief networks. That is something. Oh, sorry, I've just sent it to Gary. Why did I just send it to Gary on his own? Sorry, Gary. There we go. There's it for everyone. You should have that link. That's where the data set come from. And you can see that there's 3 publications that have used that data set. Hopefully we can become the 4th. So yeah. And it gives us the citations and whatnot, the different versions of the data set and where it's being used. So yeah, so these researchers, they're the ones who collected these images and put it for public use. So take a look there, do some reading of their papers and see what they've done. I know one of them, I think it's the second paper, they used a stain deconvolutional layer for convolutional neural networks in medical microscopic imaging. That might be a paper that might be worth looking into and see if there's anything we can take from that. I mean, the theory will be there, but it might not be, the code might not be available, so it might be limited in its use. But it seems like a a decent paper, deep learning, classification, stain deconvolution. So nice, yeah, take a look at that. So the question there, Gustavo, I'm a newbie. Is it necessary to perform data augmentation having so many images in the main data set? Now, that's a good question. Image augmentation usually serves two purposes. One, to increase an imbalance, well, not increase an imbalance, but to solve an imbalance. It can be used for that. It can be used to create more data if you haven't got enough data, but also it can be used to improve a computer vision model. Computer vision models, the more data you have, the better every single time. And, you know, we certainly do have enough images to run a model without any augmentation. However, will augmentation improve the model at the end of the day? I believe it will. The chances are it will. And another reason for doing augmentation in this particular task as well, for beginners, you're absolutely quite right. If this was a real life project, we may not have to do, we might have sufficient images to not do any augmentation. However, that's no good for us in a beginner project. We need to understand how augmentation is done and better prepare beginners to go out into the wider world. And, you know, if they come across data that needs augmentating, they know how to do that. That's the main purpose of it. But again, it will improve our model if we can create more images than what we've got. The more data we have, the better the model is going to learn. As long as, of course, the augmentations aren't too noisy, and otherwise it'll be completely useless. But that is what we're going to discover in the next couple of weeks. I hope that answers your question, Gustavo. It was a good question. Thanks for asking it. We've got 2 minutes left on this. No problem. We've got 2 minutes left on this call. Please, if you think of anything else, ask it in the Slack. Let's go away now and start researching and taking a look in what other people have done. Let's take a look at what computer vision models are capable of in a medical context. Let's steal some people's ideas, post it all in our Slack channel in the knowledge sharing thing, and let's get a discussion going. And then when we meet up at some point next week, midweek, we can discuss a plan of attack and we can start working towards that. And on the weekend call, we can basically confirm our teams, we can confirm our methods and how we want to tackle this project, and we can start putting it into practice and make a good strong start to this project. Again, thanks everyone for coming. I look forward to working with you all. Let's stay in touch through the Slack. Let's get it a busy hive of information. And again, reach out with any questions, reach out for any support whatsoever, to me, to Salman, to anyone else who you think will have the answers to them questions. And again, look forward to working with you. Thanks again for coming. Thanks for spending a part of your Saturday with me. I know it's you know, a Saturday is a nice day of relaxation, but here we are talking about science. Great. Thanks very much, everyone. I will see you soon. Thanks for coming.
Thank you.
Thank you.